gives you back a vector field. So it defines a way to multiplication. So it gives the structure of an algebra to vector fields. So think of it as multiplication. So we define the bracket between two vector fields in coordinates. So this is in coordinates to be partial y as an array, partial q. This is a Jacobian times x as an array. The result is a vector minus the other way around. So sometimes the notation in the literature is the Lie bracket is written as follows. It's written as the Lie derivative of y along x. Sometimes it's written as add the adjoint, add xy. Okay? So you will find this notation all the way. It's a little bit misleading. So this is Lie derivative of y along x. And I'll say why it's misleading. Just giving you the notation, so sometimes we have add 2xy, by this we mean x with add xy. So it's x with xy, okay? Iterated Lie bracket or multiplication. And you can have this rule as n, so this is like n, here will be n minus 1, okay? So, when you see this Lie derivative of y along x, you might think that the Lie bracket acts as a directional derivative. Directional derivative of y along x, and this is wrong. And I will show you why. But before that, let's even talk a little bit about the directional derivative. So Lie brackets are a bit weird. Why? Because both vectors got to be differentiated, not only one. The direction derivative of y along x in Euclidean coordinates or in general, this is the derivative of y. Y is being differentiated, not x. In the Lie bracket, both are being differentiated. So Lie brackets are a little bit weird in the sense they are not directional derivatives, and we'll talk about that later on more when we come to the connections and how to do directional derivatives in differential geometry. I'll give you a little bit of a glimpse here on that topic. So how to define directional derivative in Euclidean space? Because we did not also define the Lie bracket last time. So what's directional derivative in Euclidean space? It's nabla y dotted with x, right? Which is the Jacobian of y multiplied by x. So it's the first element of the Lie bracket. There is no the second term. But actually this guy doesn't perform well under change of coordinates. We'll talk about that later. Or you have already seen it. You have already seen that this is not tangent vector, so it doesn't perform well under change of coordinates. How do you write it? How do you write this definition? So nabla y dotted with x in Euclidean space. This is the limit as h goes to 0. H here, maybe I'm defining it. This is a vector field. The result is a vector, so I'm defining it at a point P. What's that? So I'm differentiating y, so I will subtract from y at P. I will perturb y, so y at P plus something, I will perturb y. So what's this thing? What's this thing? H times x. Very good. I will perturb P in the direction of x. And this is okay in Euclidean coordinates, although it's not rigorous enough because I'm adding a velocity to a point. But anyway, here in differential geometry, what is the Lie derivative of y along x? Along this line. So this is the limit of h goes to 0. Again, I'm defining it at a point P, it's a vector field. So I'm going to subtract from y P, and I need to perturb P a little bit. How to perturb P in the direction of X in differential geometry? What's the language?
The flow.
Very good. The flow from P along X for some time, T or H, the way you define. So is this a well versed or well-defined definition? What do you think? Let's have more clarification. So here is the manifold, and I have P. I have this is the vector field X, and I'm flowing along X. So I arrived at a different point here. This is phi from P for some time along X. I have the vector field Y, so this is Y at point B. When you go over there, it's a little bit different because it depends on the point, right? So this is Y at the point. And now you're asking me to subtract this guy minus that guy. And I'm asking you, is this well defined?
It's not defined because these are the first and second vector belong to two different tangent
Exactly.
spaces.
This guy lives in that tangent space at this point. This guy lives at that tangent space. Correct? So I cannot subtract. Please move one to the other.
Push forward.
I have a map here from this point to that point. What is this map?
Full back. Sorry, push forward. Map.
Let me change a different color for it because you guys would think that it maps tangent space. I'm just having a map from this point to that point. What is this map?
The inverse of the flow.
The inverse of the flow, because I can flow along the inverse of the vector field or backward in time, right? So you have a map between the points. Okay, so how can you move the vector field from here to there? By
The tangent.
by the push forward of that map. Whatever it is, I don't care what is its name, it's the start of it, the Jacobian of that map. Is there any question about that? So now this is the rigorous definition of the Lie bracket, or the Lie derivative of y along x. Any question about that? Okay. But even though Lie brackets are weird, and I still did not show you how this is the case. But
Professor, is it?
yes,
There's an H in the denominator, right?
yes, we have here h. So because we will encounter this guy many times, let's give it a definition. Give it a name and a rigorous definition. So given f diffeomorphism, so maps M to M and its diffeom, and given y a vector field on M, I will define the following map. So y at f, y composed with f, this is a vector field, and f inverse, the push forward of it multiplied by this guy gives you a new vector field. So this is what we did exactly here. So if you have M, here is M, this is P, this is F, so this is F of P, here you have Y, here I have another Y, but then when you push Y forward by F inverse star, you will get a different vector field. So this is what we call here F star Y. This is F star Y. and we give it the name, the pullback, although it's push forward, but I'm sorry, this is the standard name. The pullback of y along f. The name might be understood because I have, so first of all, here is y composed with f, and then pulling it back along f, which is equivalent to pushing it forward with f embers. Here we have the star as a superscript, so please, don't feel confused. If you have any question, just let me know. This is really the Jacobian, and this composition is just multiplication in coordinates, right? This is y evaluated at f of something. So in this language, what is this guy? What's this guy?
Pullback of y along the flow.
Very good. This is the pullback of y along what map? It's the flow of x. We will encounter this a lot. So this is phi hx star y. Okay? Let's have an example. It's not fancy under any means. I mean, you will see it's. Let's have an example. Say x is. So this is the example. X is 1 and 0. This is on R2. Y is 0 and any function of x. So this is on R2. So what's the flow along x from some point x and y? What's that? So you have the initial condition x and y. The first element you increase by t, and the second element stays as is, right? So what is y composed with the flow? This is easy. Y takes 2 points and gives you a vector. The first element of the vector is always 0. The second element is a function h. A function h of the first argument, which is x plus t. Any questions about that? If you have a question, just stop me, okay? And you don't need to write, but of course you're more than welcome. We need the inverse, which is super easy. I'll just reverse the time. And I need the Jacobian of the inverse of the Jacobian. Well, differentiate with respect to x is 1, no y, 0, 1. So this is actually identity. So here is the pullback of y along the flow of x. The definition is phi tx, the inverse push forward, which is just identity, multiplied with y composed with the flow. So it's 0 h of x and t, x plus t. And actually, according to this definition, I'll show it to you again, but according to this definition, the Lie bracket, this is the Lie bracket, right, can be defined as d by dt at t equals 0 of this guy. This is t. So you can show that when you get this pullback, here is the pullback, you can differentiate with respect to t, put t equals 0, and you will get the Lie bracket. Okay? This will be an exercise in the homework, which I will post today. Any questions about that? I did not show you yet why Lie brackets are weird and they are not directional derivatives, but I wanted to show this definition first, and what is the pullback, because we're going to encounter it
Professor,
several times.
can
Yes.
you repeat that again? Why did you put
This one?
yeah?
This
No.
one?
No, the upper one. Like, why did you put phi h minus x there? And then
Oh yeah, sure. Because here I have a vector field that lies in that tangent space.
yeah,
Here I have a vector that lies in another tangent space. These are two different spaces. So it's like you have a vector in the xy coordinates, you have a vector in the r theta coordinates. You cannot just subtract them, you need to bring one to the other copy, right? So, and how we move vectors by the Jacobian. So you need to give me a map between points and I will use its Jacobian. we have the map between points, which is the reverse of the flow, and I'm using its Jacobi. Okay? Any question about that? Again, like I said, this is what I promise you, that to be comfortable with the language, nothing more. So this is why I'm stressing the language. But any question?
Just a small tweak.
Sure.
So, the Jacobian, do we evaluate it at what point? Like at the point in the
Where?
So do we evaluate, let's say, so do we evaluate it at P or at phi?
No, this
finding
is
effects at
it's
P?
actually varying the point. The Jacobian will be varying.
Yeah, so do we evaluate?
Oh, okay, I got what you mean. So, okay, that's a good question. So the result is a vector field, which is, so this guy is function of XYZ, for example, in 3 dimensions.
Yeah.
Now you're asking at what point. I will ask you back at what point you need, because this is a vector field. A vector field will give you a vector at each point. So at that point that you need the vector field at, just use it. Okay? So this is a vector field defined on all of M. So at that point that you need it, just everything will be substituted at that point. Good question. Any other question? So everything here is symbolic. If you want a more, specific answer to your question, everything here will be just symbolic, and the substitution will be very late in the game. Depends on the point that you want. We don't substitute at f of p, we don't substitute at p, we don't substitute at any point. Any question? Okay, so we define just a new vector field. If you give me a map, typically it's a flow, and if you give me a vector field, I'll give you a new vector field. We will see why this is important later on. But at least now we know that in terms of this new vector field, I can define the Lie bracket. Okay. Let's see why Lie brackets are not directional derivatives. Let's consider this example. So again, Lie brackets are not directional derivatives. Why I'm saying that, why I'm stressing that? Because the language derivative, the language which is the Lie derivative of y, this is in all differential geometry books and control theory, geometric control, you will see that the Lie bracket of x and y is indeed written as Lxy, and it's named as the Lie derivative of y along x. So this might give you the intuition or the indication that the Lie bracket is the direction derivative of y along x. This is not the case.